High voltage, even like for a transformer, high voltage, you want to keep series coils. Low voltage, parallel coils. Same way we did on the transformer. Okay, more of the same. These types of connected. This is delta instead of Y.
Should not be confused with the reconnection of multi-speed polyphase induction motors. In the case of multi-speed motors, the reconnection results in a motor with a different number of magnetic poles and therefore a different synchronous speed at a given frequency.
That's a good point. Thank you.
Uh-huh.
All right, wound rotor induction motors, the other kind now. So why are we winding them? Because we're actually providing power into those internal windings. So a wound rotor induction motor is a variation of the squirrel cage, the cage induction motor,
Hamster wheel.
standard cage, okay.
Gerbil wheel.
They use a three-phase winding wound on the motor, which is terminated to a slip ring. Notice it's not a commutator, it's a slip ring. There's no gaps between it. It's a little easier on your brushes. All right, again, you would use this for a synchronous motor. All right, and I think that's what we're going to get into shortly. All right, the slip rings connect to the three phases startup resistors in order to provide current and speed control on startup. The motor is normally started with full external resistance, and the rotor circuit is gradually reduced to 0.
And either manually or automatically.
External resistance. The resistance is reduced to 0. The external resistance, that is.
Mm-hmm.
Okay. And again, that's similar way that they do with DC motor starting. This results in a very high starting torque from 0 speed to full speed at a relatively low starting current. The 0 external resistance, the motor, a wound rotor, motor characteristic approaching that of a squirrel cage motor. Interchanging any two of the stator voltage leads will reverse the direction of the motor. So besides that, not a lot there, but it also, I don't know why they're showing T1, T2, T3 there, but that's motor connection block on the side. They'd have leads coming out there and also leads going in there. All right, wound rotor are also used for varying speed service, using a wound rotor motor as an adjustable speed drive. The round control, the rotor control resistors must be rated for the continuous current. Makes them very heavy. Speed varies with the load, so that they should not be used where constant speed of each control setting is required. Three-phase synchronous motors.
As
Okay.
its name suggests, the three-phase synchronous motor runs at a constant speed from no load to full load.
All right. Three-phase AC voltage is applied to the stator winding and a rotating magnetic field is produced. DC voltage is applied to the rotor winding and a second magnetic field that acts like a magnet and is attracted by the rotating stator is produced. Okay, DC, AC, and believe it or not, I've seen this used in Kansas when I was down there. They had large 5,000 horsepower synchronous motors, and I mentioned it before, by overexciting the motor, in other words, providing more than what you need to maintain your synchronous speed or less than what you need, okay, you will actually add VARs or take away VARs from the grid. Okay, so they used it for controlling their voltamps reactive as way, because they were basically at the end of the grid, and it was a way to add a bunch of VARs to the system without a lot of cost. Although the motors are considerably more expensive, again, once you pay for it, then it's something that you can keep forever. DC voltage is applied to the winding, and a second magnetic field that acts like a magnet and is attracted to the rotating magnetic field is produced. The attraction between stator and rotor magnetic field exerts a torque on the rotor and causes it to rotate at a synchronous speed of the rotating stator field. The rotor does not require an magnetic induction from the stator field for its excitation. As a result, the motor has zero slip. The only type of motor that has zero slip is a synchronous motor. That's it. Synchronous motors are not self-starting, requiring a method of bringing the rotor up to near synchronous speed before the rotor DC power is applied. Okay, so once you get it up to speed with no DC applied, then you can make it a synchronous motor. Until it gets there, you can't. An electrical system lagging power factor can be corrected by overexcitation. That's what we were talking about, the synchronous motor operating within the same system. Just what we were talking about. Okay. Not going to go into it, guys, because I just want to introduce you to the concept. Look at it in your book. It's pretty well described, but again, something that unless you're working for a utility, you'll probably never run into. And that's it for this particular one. And good for now. We'll see you a bit